Hi, my name is Ling, and I'm going to talk about my work with Professor Van Wu, reaching consensus on random networks, the power of few. So let's begin with the introduction. We have a game of election. We have n people, and initially, everyone has an opinion on a certain topic. So if the topic is a country, the opinion can be whether we approve of the president. So it can be either yes or no. And every day, a person will look at the opinions of their friends and choose the majority opinion. But if there's a tie, the person will keep their opinion. And so the opinion wins if at some point everyone follows that opinion. So it's clear that after that, everyone will always follow that opinion. So that's what is a win. So we want to analyze this. So let's translate it to graph theory. We have a graph with n nodes. Initially, every node is colored either red or blue, and on each day, a node will look at the colors of their neighbors and follow the majority and keep its color if there's a tie. A color wins if at some point everyone is colored with that color. So let's consider this example. We have 3 reds and 3 blues, and let's figure out the coloring for day 1. So let's consider 1. We have 2 blue and 2 reds. So it's a tie. So it will keep its current color, which is red. The same goes for 5 by symmetry. Let's look at 2. We have 2 blues and 1 red neighbors. So by majority, it will be blue. The same for 6. Now for 3, we have 2 reds and 1 blue neighbor. So by majority again, it'll be red. And now we have 4. We have 3 reds and 2 blue neighbors. So it'll be red. That's the coloring for day 1. Now it's easy to see that everyone will turn red for day 2. So it's a win for red. But let's look at this example. Here everyone has 3 neighbors and 2 of them of the same color and 1 of the other color. And so by majority, everyone will still keep their color for the next day. So this process never changes. It's a stalemate because no one wins. But let's look at this example. Here, 3 and 4 will keep swapping their colors forever, but they're still not a winner. So it's a stalemate with a cycle of 2. It turns out that these are all the possible outcomes. It has been proven quite a long time ago that the process will always end with either a stable or a pure 2 states. Okay, so the thing that we are mainly interested in is this process on the G and P random graph. So we want to know the winner. Imagine an initial balanced state, then red and blue will win with the same probability, slightly less than half because we have to subtract the change for stalemate. But suppose in the initial state, one has an advantage, C, then it will have n with 2 plus C members. So we want to know how much the advantage be in order for the side with advantage to win with high probability. So that's the main thing that we'll focus on. Let's consider a very simple example to get a sense of it. Here we have an advantage of linear size. So it's epsilon n. And so we claim that the red wins within 1 day with high probability. So it sounds surprising, but let's try to prove this. consider node V, assume that it's red in the beginning. So define RT and BT to be the set of red and blue after they T, and gamma V to be the set of neighbors for V. So V turning red or blue if just V belongs to R1 or B1. We consider diff of V to be the difference between the number of red and blue neighbors for V. So V turning blue is the same as diff of V being negative. So we write diff of V as a sum of variables, 1 for a red neighbor, -1 for a blue neighbor, and 0 for a non-neighbor. And so it's a sum of Bernoulli variable with a factor of either 1 or -1. So note that the expectation is positive. It's just P times the advantage. And so by a Hopf being bound, the chance that it goes below 0 is exponentially small. It's also the chance that V turning blue. And by union bound, the chance that anyone turning blue is also exponentially small. So the reverse happens with almost certainty, which is that red wins after just 1 day. So it turns out that a linear advantage is so large that it guarantees a 1-day victory. But what if C is smaller? So, for example, square root of n, we can see that the previous method will give us a count of linear size, so it doesn't work as a probability bound. So it does, but can red still win in more than 1 day? Maybe. So actually the answer is yes. In fact, we proved that when C is a constant, red can win with arbitrarily high probability, no matter how large n may be. This is the power of field phenomenon. So this sounds very surprising because when C is a constant and n is large, there seems to be no difference between an initial balanced state and a state with an advantage of C, but somehow we can guarantee red wins with probability high at like 99%. But before we prove it, we'll discuss the formulation to clarify the settings, discuss the results, and also mention related results. So actually, in the proof for our linear advantage, we've been implicitly using this setting. We have red and blue being fixed, and we draw a random graph on their union. In fact, there are a few other settings that are equivalent. So the first one is we draw the graph first, and then we randomly choose the initial coloring, but we fix the sizes of the two colors. And then we can, the second one is we fix the two sides, but with an initial balanced state, and then we draw the graph over them, and then we choose C the factors from blue to join red. The third one is we fix red and blue of size n/2 each minus C each in a swing group of 2C, and then we draw a graph over them and we let the swing group join red. So it's easy to see that these settings are equivalent to the former one, but we prefer to use the former one because we don't have to worry about the randomness of the initial coloring. So we can focus on the graph itself. And we grouped two theorems. The first one is the power of field. So when P is 1/2 and we have 6 advantage, then red already wins within 4 days with probability at least 90%. The second one is an asymptotic bound. So it bounds the probability that red doesn't win within 4 days. by a term of the constant depending on p times the maximum between 1 over n and 1 over c squared. And when c is a constant, we can see that this term is of order 1 over c squared. So we can say that the chance that the red wins tends to 1 at the rate of c squared. So before moving on, I'll mention some related works. So the process has already been studied as named maturity dynamics or maturity percolation. It belongs to a very broad category of opinion exchange problems. Also, a lot of people have been studying our exact same process. But the key difference is they consider a random initial color where nodes are given initial colors independently from each other. But here we fix the number of each side, so we can give one color a very small advantage to highlight the power field phenomenon. But here, in the usual setting that they did, they have proved a result in 2016. So given a fair initial random coloring, when p is larger than lambda times 1 over square root of n, we can choose lambda large enough as a constant to get the sign with the initial majority to win after 4 days with probability at least 0.4. So it seems that 0.4 is not very good a number. We want it to be at least more than half. So here in 2019, it has been improved not just by 1/2, but it also tends to 1 as lambda tends to infinity. So it's a huge improvement. The key point here is they managed to work on sparse random graphs when p as a function of n tends to 0. But our techniques currently don't work for p being over 1. The reason is here we focus on reducing the advantage to achieve a very small constant like 6, so that we can highlight the power field phenomenon. In fact, we are also able to prove the power field phenomenon for sparse random graphs. So here we have a theorem that says that the red wins with arbitrarily high probability for p larger than 2 times log n over n, but the advantage will be at least a constant over p. So it also works when p is a constant, because the term c over p is also a constant in that case. So it does imply the power field phenomenon that we did here, but probably with a constant larger than 6, probably it could be 20 or even 100. And the techniques are different enough from our techniques, so we'll write about it in our next paper. We can already see that this theorem implies the theorem in 2019. So by Gaussian approximation, one side has an advantage of size square root of n almost surely, and assume that it's red. Then we can pick a lambda large enough so that p becomes larger, so that the advantage becomes larger than c over p. So we can apply our theorem to get the same red win. Now we've seen that when the advantage is 6 and p is 1/2, the chance that red wins is high. But how about giving red a minimum advantage? So it's 1. And we tried this experiment where we have 10,000 nodes. We had an advantage of 1 for red, and we repeat it for 10,000 times. So this is the result. Here we can see that red wins with frequency more than 93%. And even more surprising is that it only needs 3 days to win. So we proved it for 4 days. So it's very impressive. So we conjecture that the chance for red to win when p is 1/2, and given one advantage is 1/2 plus a constant delta, but the proof is still open. Another conjecture that can imply the power of field, the power of 1 is value of defectors. So we define the value of a defector from blue to red to be the probability that red wins with him minus the probability that red wins without him. So it's obvious that the last defector, the one with number n/2, will have no value because without him, red will also win with probability 1. So we conjecture that this value is diminishing with the number of the defectors. So with this, it can be proven that the delta in power of 1 conjecture can be chosen to be 0.5, 0.9 minus 1/2 over 5, which is still positive. But the simulation suggests that it can be at least 0.43, so even that is not that impressive. And here we have a few related interesting questions. The first one is an upper bound on the probability that red wins. So we know that it can be very close to 1, but we strongly believe that when C is a constant, there's also a constant bound on the probability that red wins. And we also want to compute this when P is 1/2. The second one is the probability that there's a stalemate tends to 0 when the initial state is balanced. So it seems easy to prove, but we haven't thought about it very seriously. And then the third one is to improve the number 2 in our theorem for random sparse graph. So we know that when the graph is connected, P has to be larger than log n/n, and below that, when the graph isn't connected, then red won't be able to win with high probability. And so this, if true, can complete our results to an optimal state. And there are a few other interesting settings where we can mix up any few of them and get a completely different problem. And the first one is the multi-color version. So the rules is the same, we follow the majority, but here there can be more than one guy with a majority, so we can randomly choose among them if there's a tie. Also, we can change the updating rules so that for the first one, we can update with the usual rule with probability Q, but then we can also stay the same, so it's sort of a lazy version. For the second one, we can sample only a few of our neighbors and update based on their colors only. So it's sort of realistic considering that our Facebook friends can be a few thousand, but we only follow a few of them. And the last one is when we change the graph to a random preferential attachment graph so that it models more closely to social networks in real life. And now let's prove the main results. Note that I'll only give a very rough sketch of the argument. The details will be in our paper. So actually, we'll prove a general theorem that implies both of theorems 1 and 2. It will also describe the process day by day. So it says that for the first day, red will gain a square root of n advantage with probability of 1 minus a maximum of 1 half, 1 over n, and 1 over c squared. For the second day, almost surely it will gain a linear advantage. For the third day, almost surely it will gain an overwhelming advantage where there are less than half of Tn, the expected degree, blue nodes left. And for the fourth day, almost surely it will win. So this is the main term of the probability, the one on the first day. After that, once it gets the square root of n advantage, red will almost surely win in the next 3 days. This is an illustration of the process. You can see that red increases faster and faster until it covers everyone on day 4. So some notation, RT and BT, the set of red and blue after day T, the event that U and V are adjacent, the binomial distribution, CDF of the normal distribution, CDF minus half. So let's prove for day 1. We want to bound the probability that size of R1 is less than half of n plus some v times square root of n. And so we write x being the size of R1 as a sum of indicators, each for the event that v turns red. We can write it the E and var of x using the E and var of and covariance of IU and IV for U and V being 2 different nodes. So using the Chebyshev bound, we can bound this probability with a term that involves only the covariance and expectation of IU and IV. We want this to be arbitrarily small. So if we can prove the denominator is of constant size and the denominator increases with c, we are done. So this translates to proving the covariance being bounded by 1 over n and the expectation of IV being bounded away from 1 half by d1 over square root of n for d1 that grows with c. This will be our first goal. So we use diff of v because we are trying to consider v turning red. And so note that the expectation of diff of v is positive, increases with c as well. Using a normal approximation, the chance for diff of v being positive is at least 1 half plus a term that increases with c over square root of n. And so that's the first goal. For the second goal, we want to write the covariance as a product of 2 terms of size 1 over square root of n each. We'll use a standard definition first, and then conditioning on the adjacency between U and V, we can break the first term, which is the probability that both turning red, by 4 terms, A1, A2, and B1, B2. So the same trick will work on the latter 2 terms. So the first one is A1, B1, A2, and B2. And we can rewrite the covariance as A1 minus B1 times A2 minus B2 times a constant term. So we want to bound these 2 terms by square root of n inverse. And so we use a logical trick to rewrite the probability A1 minus B1 as the probability that 2 binomial variables are equal. It is of size 1 over square root of n by a normal approximation. So we are done with the first one. The second one also the same. And so the second goal is complete. To summarize, we use a Chebyshev bound to bound the chance that we have less than n over 2 plus d times square root of n red nodes in day 1. This term will be a constant over d squared, where d increases with c, and so it becomes arbitrarily small. by exact computation, it will be less than 10% when P is 1/2 and C is 6. So that's the first theorem. Also, we'll be able to show that it is bounded above by a constant of depending on P times the maximum of N inverse and C square inverse. So that's the second theorem. So now it remains to show that red wins almost surely for the next 3 days. For next 2 days, we cannot use the argument for day 1 because we don't have the independence of the graph and the coloring. So we use this strategy. Assume that we have T as the advantage now. We fix a number below the number of blues. We bound the chance that a set of M elements on turning blue the next day. And we apply a bound, union bound over the choices of the set. Apply also a union bound over the choices of the initial coloring. So we eliminate the dependency on the coloring. So the main thing to do is to bound the chance that the set X on turning red. To do that, we use the term diff of X, which is the sum of all the diff in X. It'll be negative if everyone in X turns blue. And so we can write diff of X as a sum of independent variables. We use a Hofstadter bound, noting that the expectation of diff of X is positive. We can bound it with an exponential term where the exponent is t squared, and with t being some d times square root of n for d large enough, we can beat the double union bound to get a bound that tends to 0. So almost surely an advantage of square root of n will lead to a big advantage for the next day, in the next day. So in 2 days, we'll get an overwhelming advantage. And so with this advantage, we have less than the expected degree number of blue nodes left. And so by a Hofstadter bound, everyone will almost surely have more than double that amount of neighbors. And so they'll all turn red because they'll have more red than blue neighbors by this point. So that's the proof of the main theorem. Thank you for listening. These are the references in case you want to see.